Another application of integration is something called the washer method. Now, the washer method is really just a special application of the disk method. Instead of revolving a shape that goes all the way down to the axis of rotation, what we're doing is we're revolving a shape that stops before it reaches that axis of rotation, creating basically a hole in the center. And that's why we call it a washer instead of a disk, but the process is pretty much the same. So for instance, if we just would take maybe a function that looks something like this, and we could call that maybe x squared plus 2, and take another function like that. It's supposed to be a horizontal line, and maybe this is 1, so y equals 1. Then if we take the area between those two functions, so let's say we want to integrate it from point A here out to some point B, and we want to revolve it around the horizontal axis here, then we're revolving this shape in this region and if you notice that green region does not go all the way down to the axis of rotation. So when this green region is rotated about the horizontal axis, it leaves this hole in the center, which is why we call it the washer method. So in the washer method, we have two functions that are a part of the integral expression. The function capital R here is going to be this function that is farther away from the axis of rotation, and this function lowercase r is that function that is closer to the axis of rotation. So if we look at making our incremental rectangles, and if you think about how the disk method works, going back to the last lesson, if we just take a look at the upper function, that capital R, there is your disk method, or there is your disk for the capital R function. Let me just make that red so it's color coordinated. And so that's your outer rectangle. Your inner rectangle is that green function, or excuse me, that blue function. So that's the inner rectangle. So that inner rectangle would be that green incremental rectangle. Let me just make that green to color, or blue, excuse me, to color coordinate. There we go. And so this becomes then your r of x rotated, and this becomes your lowercase r of x, which is what is subtracted. So if we look at this tall rectangle, the red r of x, and subtract the shorter rectangle, the blue r of x, lowercase r of x, then we're left with this incremental rectangle, which represents the green area. Using the washer method with this problem, what you'll see is we have a quadratic expression and a linear expression that intersects that quadratic expression in two locations. And so if we're going to revolve this region that's bounded by these two functions, what we're looking at is that region that is created as a result of those two functions intersecting, which is this green region here. And if we revolve that green region about the horizontal axis, you can see that as we revolve this green region, we have this large hole in the center, which is why we call this the washer method. So looking at that region and setting up our representative rectangle, we see that the upper portion of that rectangle is lying on that quadratic expression, and that is going to be our capital R of x. So that's going to be our 6 minus 2x minus x squared. And the lower portion of that rectangle is lying on the line, so that's going to be our lowercase r of x, and that's going to be our x plus 6. Now, in order to write the expression for the integral, to use the washer method, we're going to need the limits of integration. And the limits of integration come from these points of intersection of the two functions. And so if those two locations are where the functions are equal to each other, then we can find the values by taking these two functions and setting them equal to each other. So we're going to go ahead and take our quadratic function, 6 minus 2x minus x squared, and set it equal to our linear function, x plus 6. And as we solve this, I'm just going to go ahead and move everything to the left side. I'm going to add the opposite of x. I'm going to add the opposite of 6. I'm going to go ahead and subtract that. These two equal 0. These two equal minus 3x. Bring down the minus x squared equals 0. This is still a quadratic function, so I'm going to go ahead and factor that to solve for the two values of x. So I'm going to factor out an x. And then I can set those two expressions equal to each other. So x equals 0, that's this point of intersection here. And when we solve this expression for 0, we get x equals negative 3, which is that location right there. So now we have the limits of integration. We can go ahead and set up the washer method for the volume. So we're looking at the volume being pi from the lower bound of negative 3, that's the left hand, that's the left limit, or the left intersection, and the upper bound of 0. And our big R of x is, again, our quadratic, that's our larger function, so we're going to have 6 minus 2x minus x squared, and that all has to be squared, and minus our lower function, which is our line, x plus 6. And that has to be squared. And we'll cap off that expression with a differential of dx. So there's our differential expression that we need to integrate. If you notice, we have a quadratic squared, so we have to FOIL this to expand it. Here we have a linear expression squared, so we'd have to FOIL that to expand it as well. Certainly you could FOIL both of those and combine like terms and integrate that by hand. That is certainly something you should be able to do. I'm going to go ahead though and show you a way to integrate this on your calculator. That is actually pretty neat. And what I'm going to do here is calculator open again. There we go. You can type this into your fint key if you would like to, but another way you can do this is to actually put the functions in for y1 and y2. So I'm going to actually put in 6 minus 2x minus x squared. And for function y2, I'm going to put in x plus 6. And since those are stored in y1 and y2, I can go grab those from our y vars function. You can see you can grab those. So when I do the fint, I'm actually going to just grab those and square them. So I'm going to go ahead and do our math 9. That's our fint function. Oops. Go ahead and get back to the main screen. Do math 9. Get our fint. And now I can go ahead and just go into vars and grab our y1 and square it, and then subtract, go back into vars, grab our y2 and square that. So in this expression here, we have y1, which is this quadratic function, squared. We have y2, which is this linear function squared. Our integration, our variable of integration is still a variable x. That's what's written in our y1 and y2 functions. And then our limits of integration are from -3 to 0. And so that's a nice compact way to integrate without having to write these functions and worry about all of the parentheses and the syntax and everything. So we hit enter here, and we get 48.6. So the answer then, and you notice that fint is without the pi, so the answer then is pi times 48.6. If we would convert that to a fraction, we get 243 over 5. So we're looking at 243 pi divided by 5 for an exact answer. Cubic units. For this last example, we have another quadratic region, 2x squared, and that quadratic region, when bound by the lines y equals 0, which is this blue line here, and the line x equals 2, gives this region right here, and we're going to revolve that about the y-axis. So if you remember back to the last section, if we're going to revolve something about the y-axis, we're going to set up our incremental rectangle perpendicular to that. So this is going to be a dy problem. And so looking at that expression then, we're looking at this region right in here in purple, and setting up our incremental rectangle for this region would look something like this. And so with this incremental rectangle here, you notice that when we rotate it about here, again, we have the hole in the center. That's why we call this the washer method. So we'd end up with the other portion of the washer right about here. And since this is the axis of rotation, then the large function r, capital R of y in this case, since this is a dy problem, is going to be this function here. Since it is farthest away from the axis of rotation, and the lowercase r of y is going to be this function here, since it is closest to the axis of rotation. So that being the case, our capital R of y is going to be the function x equals 2. Or what that really means is just that our R of y equals 2. Our lowercase r of y is going to come from the quadratic function y equals 2x squared, and solving this for x so we can get it in terms of y is going to make that look like y divided by 2. That equals x squared. And square rooting both sides gets you the option of having a plus or a minus as an answer, but graphically we see that we're dealing with a positive root. So solving that to get the function in terms of y is going to be the positive square root of y over 2. So that's going to be our lowercase r of y. And then the limits of integration are going to go from here. We're going to stack washers up from this location all the way up to this location up here. And so we know that this location is a value of 0, and this location we can see is a value of 8. And to confirm that, what we really should do is set this quadratic equal to this line here. So we're going to take the quadratic y over 2 square root, and we're going to set it equal to the green function 2. And when we square both sides, we're going to get y divided by 2 equals 4. And then multiplying both sides by 2, we're going to get y equals 8. So we know our limits of integration then are 0 to 8. And so as we set up this washer method to find the volume here, we're going to have pi and our capital R of y, which is just the value 2. X equals 2, so it's already solved for x for us. So we're going to have 2 squared minus our lower function, which is y over 2 square root. And I'm going to have to square that as well. So here's our capital R of y squared minus lowercase r of y squared. Cap those off with some brackets and add our differential dy. And we're going to integrate from 0 to 8. So there is that expression. And this actually is a pretty easy one to integrate by hand, so we'll go ahead and integrate this one by hand just to keep fresh with our integration techniques here. So 2 squared is 4. Squaring this radical leaves us with just what's underneath, y over 2. And to integrate this expression, we're going to have 4y minus y squared over 4, right? Because the integral of y is y squared over 2, and it's already over 2. That gives us our y squared over 4. And from 0 to 8, it's an 8, believe it or not. It's just a little messy. There we go. And as we then plug in the values for the upper and the lower limits, we have 4 times 8 minus 8 squared over 4. Minus, and then plugging in 0 gets us 0 for everything. And so we have 32 minus 64 divided by 4. And one thing I did notice, don't fall into this trap that I just fell into here, but we also need to cap all this off and remember to bring this expression of pi along with us. Otherwise, we're going to leave that pi out of the answer and we're going to get burned, because if it's a multiple choice question, I'm sure there's an answer there without pi. So simplifying this, we're going to have 32 minus 16. That's what 64 divided by 4 is. So our answer is 16 pi cubic units.